Welcome to this AQA AS Unit 2 June 2013 past paper. Now, this particular question is asking us about transverse waves. Now, we're obviously given the we're given the diagram or the sketch of this wave, and there's a couple of points that we are given. Now, I'm going to just tell you them, just in case you can't see them. But obviously, no, they're online. Okay, so we've got point A, which is at the top of the first sort of curve, if you can call it that. B is where the first intercept occurs, okay? And C is where the second intercept occurs. Obviously, as I said, you can see that online. And the wave is travelling at right angles to how it oscillates. So obviously, that's how we know it's a transverse wave. But I'm just kind of assuming that he picks up on that, okay? Right, so the first question, 6A, is split into two parts, obviously part 1 and part 2. Part 1 asks us to state the phase difference between A and B on the wave. So what we have to look at is the distance between them two in relation to the entire wavelength, okay? And we know one wavelength is 360 degrees, which is 2 pi. So if it's 360 degree out of phase or one complete cycle, then it is what we call 2 pi out of phase. And they are related as such ratio kind of thing, okay? So therefore, we'll look at 2 points on the wave. Now, this is 2 pi. So from this point A to the next peak, okay, that is a 360 degrees out of phase or 2 pi, okay? So therefore, if we look at, so that's that's a 2 pi out phase, okay? So if you look at halfway, well that's that point, and then we halve it again to get to B. So therefore, between A and B, they are pi on, well, that's pi, so A and B are pi on 2 out of phase. Let me just double check that. Yep, so I obviously did trust myself, but you know. Okay, part 2 says, state the phase difference now between A and C. Well, as I said, this is 2 pi out of phase, so we halve that gets to 1, but we've gone past C. So C is halfway between pi and 2 pi, so obviously, therefore it's 3 over 2 pi out of phase. Okay, so that's just a little kind of tip really for working out the phase difference. Now, if we knew the actual, wavelength, etc., we could work that out in terms of using the phase difference formula, which is 2 pi d over lambda, d being, oh sorry, is that right? Just double check. Sorry, I do apologise. So you could use the full phase difference equation. Now, just wondering whether to waste a few seconds looking it up. No. Okay, so there's a full, sorry, I do apologise. I think that is right answer, but for the equation, but I don't want to say something and then it'd be wrong. So do check on the formula sheet for the correct equation for phase difference, okay? But as I said, you could just look at it the way I did, really, for this kind of event, right? The next question, so that's part A, that's part B, next one. Next one is actually it's simpler than you think, it looks, and anyway, describe the motion of the rock particle at point B during the passage of the next complete cycle. Now you don't need to say, specifically it goes trough, 0 displacement, maximum displacement, 0 displacement, negative displacement, and go on and on, okay? The mark scheme just states, obviously it's only a 2-mark question, so the first mark is for saying, actually mentioning that it is a transverse wave. So in other words, you have to mention that the direction of travel is at right angles to the direction of oscillation, because it's going up and down as such, and it's going right. So say that's at right angles. Okay, and then the next mark you would get was just saying it moves from obviously 0 displacement to maximum to 0 to maximum to 0 to maximum, which is kind of just contradicting what I said. But really, you just say it oscillates to extreme equilibrium, whatever you want to say it as, okay? So that's 6B. Okay, so I just put that down 2 points, as I said, you need to mention that it's a transverse wave, and so obviously therefore you talk about what that implies in terms of it. It oscillates at right angles to the direction of travel of the wave. Okay, so it's told you there. I haven't just wrote it down, by the way. It does tell you that on the exam. Otherwise, I might have given something away there. Anyway, so as I said, it's a transverse wave, and the other point is actually for stating its motion. Okay, so you can see how easily people would only get 1 mark there. It's quite a mean mark not to give you, to ask you to state that one as well without actually mentioning it. Okay. So the next part, 6C, says a scientist detects a seismic wave that is polarised. State and explain what the scientist can deduce from this information. 2 marks. Now, one of them should be straight away. Now, the first thing I need to mention is what a polarised wave is. Okay, so we just say it's a wave that oscillates on one plane. So what we mean by this is obviously that's the vertical plane up and down. That's the horizontal plane, left and right. Okay. And obviously you've got all these other, versions of the horizontal and vertical plane. But, okay, so it must be polarised. It must only exist in one of these 2 planes. Okay, so it must either be fully horizontal or only act in the vertical plane. But to have it change from acting in both planes to acting in one plane, it must have therefore been a transverse wave. So you need to mention that as well. You need to mention, so the 2 marks, one is for stating that it is a transverse wave, because to be polarised and acting in one plane, it must have been acting in 2 planes before, so therefore it must have been a transverse wave to be polarised. In other words, it can't be longitudinal. Okay, so really that's what you need to state. I was going to go through writing all the points, but simple frequencies, I can't be bothered. Okay, the frequency of the seismic wave to be measured is 6 Hertz. Okay, so whenever you get a question that's asking you to calculate something, always write down what you're given. So the frequency, we are told, is 6 Hertz. Okay, deduce the frequency of a progressive wave. Okay, well, we just use sorry, I do apologise. Oh, sorry, not determine. Sorry, it says define the frequency, not determine. That's why I was looking at that going, what? So we have to determine the frequency of a progressive wave. So you just say it's the number of cycles per second, or you could just state the formula, which is obviously because c equals f lambda, lambda being the wavelength, f being the frequency, c being the speed, you could say just f is equal to c over lambda, or speed of light over the wavelength, or speed of the wave over the wavelength. Okay, so either of them 2 would have been acceptable. 6D part 2. Okay. Calculate the wavelength if its speed is 4.5 times 10 to the 3 meters per second. Okay, so we also know the frequency of that wave is 6 Hertz, so that's the speed. I'm going to label it as C, you can label it as V, and what we're going to do is apply this equation, okay? Maybe obviously not to find the frequency, but we want to find the wavelength, because we know the frequency and the speed, which is, frequency is 6 Hertz, the speed is 4.5 times 10 to the 3 meters per second. Okay, and we want to work out the wavelength. So we use this c equals f lambda, lambda being the wavelength. Just simply rearrange to get the wavelength, or lambda. Okay, so that gets you the speed over the frequency. Okay, so therefore, if I can actually write English properly, it's 4.5 times 10 to the 3 meters per second over the frequency, which we know is 6 Hertz. Okay, so you knew that. And then you just slam that in your calculator, can't speak anymore, slam that in your calculator and you should get a lambda of 750 metres. Now, when I did this question, I was put off by the fact that the wavelength is such an extreme value. Generally, it will only be, generally wavelength is what measured in nanometers, because the wavelength of certain waves are so small, but obviously this wavelength is quite enormous. Now, don't be put off by the fact it's so big. I mean, generally, when you get a value so big, it's likely to be wrong. But because we're dealing with the speed as such a big number and the frequency as such a low number in response, because it's 4.5 times 10 to the 3, well, that's something like 45,000 or whatever it is, can't think off the top of my head. And if it's only got 6 cycles per second, then it's obviously got a very long wavelength to travel such. If it's going so fast, it must also be travelling such a big distance in terms of the wavelength to actually get such a small frequency. Okay, so hopefully that kind of explained why we've got such a big lambda. Sorry. Okay, so that's the end of question 6. As you can see, all of this, I mean, what put me off about this question is we've got a graph here, and that I'm not too happy with seeing them kind of graphs. So we'd have to work through it, because I got to the end of this question, I thought, I've not done enough with that graph, there must be something I'm missing. Whereas, as I said, most of this question was just asking you to talk through your theory behind it, okay? So it's nothing too difficult. Alright, so thanks for watching, and we'll see you in the next question.